Waves and particles. So far, we've found that light has to be described sometimes as a particle and sometimes as a wave. Newton first described light as a group of corpuscles or particles and was able to explain reflection, refraction, and dispersion. Thomas Young and others found a wave-like description was the only way to explain diffraction phenomena or interference phenomena. James Clerk Maxwell described light as perpendicular magnetic and electric fields that propagated together as a wave. Einstein brought back the particle model to describe the photoelectric effect, and then Arthur Compton used the particle model to explain the frequency shift of photons when they scattered off of electrons. Well, physicists love symmetry, and it was found that light had both the properties of a wave and of a particle. Well, so far, matter, in particular electrons, were well understood as particles. Would it be possible that maybe they also had wave-like properties? That would give us the kind of symmetry that physicists like. Well, what about it? Can matter be described as a wave? Since light had been described both as waves and particles, Louis de Broglie in 1924 proposed that particles could be described as waves with a wavelength equal to h over p, where h is Planck's constant and p is the particle's momentum. This is the same equation that Compton used to determine the momentum of a photon. Thus, all particles, and by extension objects like baseballs and bowling balls, have a de Broglie wavelength associated with their motion. But since h is so very small, the wavelength associated with large objects is vanishingly small. However, for very, very small particles, like electrons, their wavelengths are often 10 to the negative 10 meters, which are about the size of an atom. So one might expect that they could experience wave-like effects like diffraction and interference. De Broglie proposed that an interference experiment be set up with crystals and electrons to validate his theory, but no one tried until decades later. In 1927, Clinton Davison and Lester Germer were studying how electrons bounce off a nickel surface. During the experiment, an accident occurred that resulted in scarring of the nickel surface, making it act like a three-dimensional diffraction grating. They were startled to find an interference pattern in the scattering. It was as if the electrons were diffracting as waves. This turned out to be the first experimental proof of de Broglie's hypothesis. Later on, the two-slit experiment that showed light was a wave, as performed by Thomas Young in 1803, was replicated with electrons. In this experiment, the de Broglie wavelength of the electrons was on the same order as the distance between and the width of the two slits. Electrons fired one at a time towards the two slits show the same interference pattern on the screen as photons had in Young's experiment. This indicated that something like an electron wave must go through both slits at the same time, which is something we can't imagine a single particle doing. This result has been verified over and over. Let's look at the photos of electrons being fired one at a time through two slits. Each one of the exposures, A through E, was made after a slightly longer time. When you look at photos A and B, it appears as though the particles, the electrons, are interacting with the photographic film at one point as if they were a particle, leaving simple spots. But as you watch the trend over time, you begin to see a pattern set up, and that pattern becomes very, very clear in pictures D and E. The electron must be traveling as a wave as it goes through the slits. Otherwise, this diffraction pattern wouldn't set up. And yet, when it interacts with the film, it simply interacts as a particle. So, in this sequence of pictures, we actually see that electrons act both as a particle and as a wave.